All right. So today we're going to talk about these things called permutations and combinations. And basically both of these are different ways of counting arrangements of things. Okay? Or counting how many groups we can make of things. So, give you a quick example. As many of you know, I like to collect Star Wars action figures, and I have a few of them here today with me.
Oh my goodness.
So, and I'll learn you guys some names here a little bit too. So this is, who is that?
Starts with a B.
No.
He got his arm chopped off.
Who is that?
Yeah. Yeah, in the fourth one.
He's got a butt.
His name is Panda Baba. Panda Baba. He was hanging out with Dr. Evanson in the cantina. All right. Who's this guy?
He's a bounty hunter. That's all. Dengar. It starts with a D.
It's not Dengar. It's not Dengar.
He's a bounty hunter.
He's a bounty hunter.
No, Bosch. It's like Bosch.
Bosk. With a K. That's Bosk. Okay. And you should know this one. That's Yoda. Okay. So let's say, gonna keep it simple here, all right? So I've got just these three action figures, and I want to display them on my shelf at home. But I want to know how many different ways could I arrange them on my shelf? Okay? So how could I figure that out?
9 ways.
9 ways?
Yep.
How do we know? How do you calculate that? No, I just want to know, of these three, I could go Panda Baba, Bosk, Yoda, or maybe I want to go, the pattern. So maybe I want to go Bosk, Yoda, then Panda Baba, or maybe I want to go Panda Baba, then Yoda, then Bosk. Like, how do I count all those different ways of how I could arrange them? Yeah.
Well, you take one and you go in 3 different places. Times by 3.
Mm-hmm.
Add it. So you do that for all of them and you add them together. But there's probably a simpler way.
So you're thinking 9 then? Because you can go 3 different places for the one guy, 3 different places for the other guy, 3 different places for the other guy. Well, if you do that though, is when Bosk or when Panda Baba is here, there's only 2 different places these guys could go, not 3. So you're actually overcounting it a little bit there. There's 6. Now think of it this way: instead of counting with each individual action figure where they can go, think about each individual place where they sit. Okay? So like if this is my shelf on my wall, a spot, you don't have to. I got a spot for one guy, spot right here for another one, spot right here for another one. If I'm reaching into my bag of these 3 guys, how many different action figures could I put in the first spot?
3.
I got 3 different options, right, that I could pull out and put up there. Okay, I've already got one up. It doesn't matter which one, let's say Yoda, but whichever one I pick the first time, no matter what, how many am I going to have left to choose from? 2. Okay, I picked that one. Now, no matter how many or which combination I picked, no matter what, how many do I have left to choose from? 1. Okay. 3 times 2 times 1, 6. 6 different ways to do it. Okay.
That's not how it's going to work. Yeah.
Yes, it will.
No, you mean like adding?
No, the adding won't work. The multiplying works.
That's what I was saying. No, Caleb said adding. No, that's a lie. Caleb said adding. That's not true. At least somebody
All right, now, this is assuming, now what you guys have just calculated is you've calculated a permutation here. Okay, and this is assuming I'm going to use all 3 of them. Okay, but sometimes maybe I have, like I have a collection at home of about 700 of these, and let's say, yeah, and let me actually use this to teach you something for just a second. So I have 700 of these at home, but let's say like somebody wanted me to come and like display some of them for something, but I can't bring all 700. Like maybe just bring like 20 out of your 700. Anyway, so if I was going to come and bring like just 20 out of my 700, how many different combinations or how many different arrangements of 20 out of my total of 700 could I choose?
Well, you have to do like 700 times 699, and you have to do it all the way down.
Wait, how much are
You would, yeah, basically, so I'd have 700 choices for the first spot, 699 choices for the second spot, all the way down to the 20th spot, right? If I was just taking 20, I wouldn't go all the way down, right? Because I don't want all 700, I only want 20 of them. So I got to do so there's still this multiplying thing going down 1 each time, kind of like we did here. But I would stop after a little ways. Now there's a formula for that, where you don't have to sit there and actually multiply all the way down. No, you can't. Sorry. But, yeah. Yeah. I'll field questions later. We're still recording and such here, so let's actually do some math. All right.
I got Commander Cody in my basement. He's on a truck.
So let's say I'll switch to something else. Let's say I have 20 really nice.
Why did you have a really nice?
Because you wouldn't want to necessarily do these.
Yes, now we're talking. I was gonna write. I don't like baseball.
So let's say I got 20. Like I got tons of baseball cards, but I got 20 that are like my really good ones, and I display those 20 really nice baseball cards. How many different ways could I do it?
Pythagorean theorem.
All right. So do you see, guys? Shh. Do you see how this is really just the same type of question as the last one we just did? Okay? So think of it as like I have 20 spots that I need to arrange them in, and think about how many choices do you have as you go down. So it would be 20 times 18 times 18 times 17, yada, 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 times 3 times 2 times 1. Okay? Now, you could take out your calculator and just start multiplying and doing all of that and figure it out that way. There is, however, a button on your calculator that will do a multiplication like this, and all you have to do is type in the 20. And it'll get all of it for you. And it's called, hold on. It's called,
Oh, I see it.
looks like this. It's an exclamation point. Yep. You to find it. So here's where you can go get it. So if you go to math, over to PRB. What do you suppose PRB stands for? It's a probability menu. Okay. See the exclamation point, number 4? So you got to type the number in first before you jump into this menu. But if I want 20 factorial, I do 20 and then math over to probability down to the exclamation point. So how can I arrange those baseball cards? A lot. A lot. Think about that. That's a really, really huge number. 20 times 19 times 18 times 17 times 16, all the way down to 1. I mean, you're multiplying, by the time you start multiplying numbers that large, that many of them, it's going to get really, really big. So this is, yeah, somewhere in the, well over the trillions. You get bigger, you get big enough, and your calculator can't handle it. It just says overflow error. Like, there are too many numbers, it's overflowing, I can't do it.
How do you do it for like one of the ones with your 720?
You would never really be able to calculate that. It's too big.
So if you had, so you can only do that if you want to do how many ways can I arrange them? Not if I had like 20. Like
You
you had like 700, but you only wanted, you had like 20, so you could only go down to 20.
Oh, I'd have a very small number out of my 700 to be able to actually get an answer for that. But in any event, we'll get to that in a minute. So this is 2.43 times 10 to the 18th ways of doing it. We're counting how many different, or that many arrangements, if you want to think of it that way. So let's get the same question now. Let's say I have 20 really nice baseball cards again. So how many ways can I arrange Okay, so think about how that would change how we do this then. So instead of having 20 spots to display them, I have only 5, right? So how many choices do I have for the first spot? I still got 20 cards, right? So I have 20 options for that first spot. So 20. The second spot? 19. Going with this, right? I can only do 5. So 20 times 19 times 18 times 17 times 15. Okay? 16. Yeah. Haha, fooled you. Okay, so that we can type up without too much trouble. It's still going to be big, though, yeah. So this is 1860480. So it's still about 1.9 million different ways to do that.
I'll count them all up when I get home.
You do that, and we'll see you in a couple of years. All right, now, there is a formula for this because depending on how many of them you want to choose, it could still be a lot of numbers you got to multiply together, right? You know, what if I had, 20 really nice baseball cards and I wanted to do like 15 of them or something? Well, I still got to, that's 15 numbers to multiply. There's a shortcut. So this right here, think about what we just did. On the entire, all the way down to 1, okay? We only took that of it, okay? We left off all of this. Well, what is all of that? That's 15 factorial, right? And the entire thing was 20 factorial.
So do you 20 factorial minus 15 factorial?
Well, almost. It's not exactly that. So it would be the 20 minus the 15. So the entire thing okay, now not exactly that because this is all multiplying, right? So you're actually taking the total and you're dividing out this bit, right? So what I came up with here was actually 20 factorial divided by 15 factorial. Does that make sense? Because it's all multiplied together, right? To get you 20 factorial. You take that 15 factorial, because it's all still multiplied, right? You'd have to divide that away. Not really subtract, divide. So it's 20 factorial, the big number, take away, or divide away that other piece that you're not using of it, and there you go, okay? So if you do, try to look on your calculator, do a 20 factorial divided by 15 factorial, should get you the same answer, that 1.8 million, whatever, okay? This is part of it. It's not all of it. So here's some notation stuff for a permutation, which is what we just did. So permutation looks like this. It's big P, little r. And the little n and the little r are going to be numbers, depending. The n is how many things do I have to choose from, and the r is how many of them do I want to choose. So like in the baseball card example we just did, what's the n? 20. What's the r? 5. Out of 20, I want to choose 5 of them. Okay? So this is the total amount, and this is how many we pick. So that formula that we just came up with, we did 20 factorial divided by 15 factorial. So 20 factorial 20 for that example, right? So it's going to be n factorial on the top, 15 from 20 and 5. N minus r. Factorial, though, right? So on the bottom, it was the n minus the r factorial. That's the formula for a permutation, okay? So if I have lots and lots, I don't need to sit here and try and multiply it all out by hand. I can follow that little formula and do it, okay? So let's try one. Jump to the next page here. So let's say we've got 10 horses running in a race. So how many ways can 3 horses finish first, second, third? Do you see, like with my baseball card and with my action figure examples, this is really kind of the same thing? It's an ordering of stuff. When I'm putting things out on my shelves to display them, I have a specific order that I'm putting them out on. Okay? Well, when horses finish a race, first, second, third, there's no ordering to that, right? One horse finishes first, and then the second place, and then the third place. So it's the same idea. It's a permutation. Okay? So what would this be then as a permutation? Using the little notation, what would it look like? Well, I'm just doing the notation first. So 10p3 would be this one then? Okay, so now, I think is what you guys are trying to explain to me. How do you calculate that then? Yeah, over 10 minus 3 factorial. Okay, so that would be 10 factorial over 7 factorial. So what do you get? So it should be 720, right? Okay. It's very normal, and we've seen this already, for permutations to be very large numbers. They end up being a little bit bigger than you probably think. There are lots of different ways that you can arrange things. Even if you have only 10, and you want to know how many different ways can you go first, second, third in that order, it's still 720 different ways that can happen. Okay? So, combinations. There's a bit of a misnomer here. People always think about those little combination locks, like on your lockers and stuff, right? Does the order matter when you're doing a combination on a combination lock?
Yeah.
Yes. In mathematics, combinations, the order does not matter. This many things out of that many. That's it. So in like my action figure example, I've got 700 action figures. I pick 20, but I don't want to display them in a specific order. I just want 20. So how many different groups of 20 could I pull out of my 700? That would be a combination instead of a permutation. I don't care about how I display them when I'm done. I just want this many out of that total. How many different looking groups could I have? Okay? So you have to count ask yourself when you're dealing with these types of problems, does the order in which I pick them matter? If the order matters, it's a permutation. Like the horses finishing in a race, first, second, third. Okay? So maybe like the top 3 horses in a race all get a treat. So how many of horses getting a treat are there? Well, it doesn't matter who was first, second, or third, right? All 3 of them are going to get the treat. That's a combination, not a permutation. Okay? So we got to be careful about that. So to do let's do a quick example here. What I'm talking about. So we're going to count the number of combinations of, let's pick 2 letters chosen from A, B, C, D. Now this one is actually small enough for you guys could just write them all out. So that's what I want you to do, is to make a list this time. Okay? So what are all the different combinations of 2 letters you can get from A, B, C, D? See if you can snag them all.
Can they be like the same, but like,
Go ahead and write both of those down for now.
and then can they like repeat like AA?
No, you can't use the same letter twice. That's a good question too. All right, so what I have there is a list of all the permutations. I did all the different orderings of 2 letters I could have. That's more than I need for my combinations, though. Combinations, remember, the order doesn't matter. I just want to have the same group of 2. So there's some overlap here now, right? There are some we could kind of cancel off because they're technically the same thing. Anybody see any in there that are the same thing? All right, I've heard someone say this one. These 2, while they're different permutations, they are the same combination. It's an A with a B. Doesn't matter which order they go, it's an A with a B. So take one of those and get rid of it. We don't need to count that one. So other ones that you guys see. Somebody raise their hand and tell me. Yeah, Teresa. BC and CB. These 2 are the same, so we can nix one of those. Okay. AC and CA. Okay, so we got one here, one there, so we can get rid of one of those. DA and AD, those are the same, so we can get rid of one of those. Yep, so we can get rid of one of those. And then CD and DC, get rid of one of those. Okay, so in this example, it doesn't always work out this way, but in this example, we've effectively eliminated half of them, right? So, how many 2 letters can you choose from A, B, C, D? There's 6. Okay. Now, there is a formula for combinations as well as permutations. The permutation one, we were able to kind of talk through why it is the way it is. The combination one is a little bit more complicated, so I'm just going to tell you, just show you what it is, and then you can follow that. So it looks like this. And the N and the R mean the same thing again, except this time we use a big C instead of a big P in the middle. So it's going to be n factorial on top, but then you divide by n minus r factorial times another r factorial. So do combinations always end up larger or smaller than permutations? Smaller. Does the formula make sense then? Why that would be? We're dividing by more, right? When you divide by more stuff, your answer is going to be smaller. It's going to be less. So you're going to get fewer combinations of, or fewer ways of doing something, okay? So let's example here now, and do a combination problem. So let's see. So let's say we're making a sandwich. You choose 2 toppings from a group of 8. How many sandwiches could you have? Do you see how this one is a combination rather than a permutation? I'm picking 2 toppings to go on my sandwich. Does it matter what order I pick them in? Now, some of you guys might say, yeah, because the sandwich might kind of, feel different when I eat it, but come on. If you've got the same 2 things on there, it doesn't matter which order they actually went on. You're still getting the same basic taste out of the sandwich when you're done, whatever. So, it's a combination, okay? Whether the pickles came first or the mayonnaise, whatever, it's the same thing. So, 8 though, so how many ways could I do that? Well, 8, that's N. I want to pick 2 out of that 8, that's R. So I those and put them right in that little formula then. Okay. So it's going to be 8 combination 2. Be 8 factorial divided by 8 minus 2 factorial times 2 factorial. Okay, and we can kind of break this down a little bit, I guess. So 8 factorial over 6 factorial times 2 factorial. All right, so try that on your calculator once here. So, yeah, I got 28. We all get the same thing there? Just be careful when you're dividing there that you have those in parentheses, 6 factorial times 2 factorial, because otherwise it's going to think you're multiplying outside the fraction with that last one. But should come out to 28. Is that the correct way? So now, whether order matters, permutation, or order doesn't matter, combination, we can do probabilities with this stuff too. And it's actually pretty simple. So if you want to know, like with this one, what would be the probability of having one specific type of sandwich? So I'm just going to randomly pick 2 toppings. What's the probability to pick the 2 toppings I actually wanted? Well, there's only one success there then, right? So it would be one success out of a total of how many different types of sandwiches? 28. See how you can easily turn these into probabilities? 1/28 would be your probability then. So it's always 1 divided by whatever you counted using your combination permutation. The only real trick is going to be determining, does the situation need a permutation or a combination? If you can pick that, you can figure that out. It's usually pretty smooth sailing from there. So see if you guys can catch on what we need for each one. So first example. We're looking at the yearbook, and there are 14 that the editors are looking at choosing from. So the editors choose 2 photos out of 14 to put on the cover. And you and your best friend both have your photos in the little group of 14. So what is the probability that you and your friend's photos are both on the cover? All right, so we're choosing 2 photos out of a total of 14 to put on the cover. What's the probability you and your friend's photos are both on the cover of the yearbook? So, is this a permutation or is this a combination? Right, because does the order that the photos are chosen matter? No. We just want to have them both on the cover. Now, what's the probability that my photo comes first and my best friend's photo comes second? Permutation then. But we just both want to be on the cover. We don't care who comes first. So 14, 2 is what we would need there then. So 14 factorial over 14 minus 2, so 12 factorial times 2 factorial. So that should be, double check my math here, but should be 91. See if you get the same thing. Question? Yep.
If we don't do the 14C2, would you mark us off for 20?
No. That, though, kind of helps you remember what you're doing, though, before you start writing out the formula, but technically it doesn't matter. All right, so we all get 91? Those of us that punched it up. Okay. So what then is the probability that we're both on the cover? Mm-hmm. Yeah. How good you look? Well, that could change the probability then. It'd be a weighted probability then. Ooh. That's something, I wish we had time. We could talk more about that. Because certain people have a better chance of making it, so then you have a % chance for each person that's different than another one. And, oh, yeah. Probably would seem that way. This one we're going to talk about. Parades are fun. Everybody likes parades. So, your soccer team. All right. In the parade. And you want to float is float with the school chorus is actually second. I'll show you a way around them. Okay, so you want to know, out of the 12 floats, what's the probability that your is in the front and the school chorus is second? Because there's a girl in the choir that you think is hot, and you want to make sure that they're in the float right behind you. So how do you decide? Or what's the probability? How do I figure that out? Is this a combination or permutation then? permutation, right? Yeah. Well, maybe. But, okay, so anyway, it's a permutation because the order matters. You want to be first, you want the chorus second. So it's going to be 12 permutation 2 then, or 22. Formula for that, it's going to be 12 factorial, and then it would be 12 minus 2, so 12 factorial over 10 factorial. And so that's going to be 132. The 10? 12 minus 2. Because the formula is n factorial over n minus r factorial, so you got to make it a 10. Did you do 12 over 2?
12 over 10 times. No, 10.
We're doing a combination. I got it. Okay. Yeah, permutation, you don't have to multiply in the denominator again. So should be 132 different floats. So if you want it to go specifically, you first, chorus second, it's going to be a probability. So there's one good way to do that out of 132 different permutations. So 1 out of 132. So that's all I got. Think you guys can handle this stuff? Okay. Let's do it.
Well, I'm guessing the